Thank you, sir.
Yeah. So let's move to today's class now. So we've looked at MOS capacitances, and we've looked at MOSFET also as a capacitance, where we said that the high frequency behavior and low frequency behavior of a MOSFET capacitance would be same. You remember this? We talked about this not just in the last class, but also in the office hours, and at much length and in much detail. So why is that the case? Because there is a source and drain region, which is a cache of charges right next there. So if you need more electrons or holes, whatever you need, you will get them from that region. So even at very high frequency, the change in charge density would happen only in the inversion layer. But then this till now is about the gate capacitance. In reality, MOSFETs have many more capacitances. MOSFET transistors, yeah, MOSFET is a transistor. So MOSFETs have many more capacitances. Are you able to relate to this perspective view of a MOSFET?
Yes.
So where all do you think you will have capacitances when you look at this 3D structure?
So we'll have some overlap capacitances of gate and source, gate and drain.
Okay.
And then we will have some junction capacitances from source to body and from drain to body.
Okay.
And from gate to channel, there would be capacitances.
Gate to channel to MOSFET, MOS capacitance जो हमने देखी थी वही हो गई. Am I right?
Yes, sir.
Okay.
Sir,
are there any other capacitances here?
Wherever there is a change in medium, sir. I'm like, whenever there is a change in medium, then we would have some capacitance over there.
Okay.
So contact gate capacitance will also be there.
Devajit, दोबारा से contact and
gate.
Contact and polysilicon gate. Okay.
Yes.
Good. What else?
Depletion.
Mother?
The depletion capacitance when there is an inversion.
Yeah, depletion capacitances, we already, Gagandeep also mentioned that the source and drains will have their junctions, and that junction would lead to capacitance. That is what you're talking about?
One capacitor, there is an inversion, this inversion is like.
Yeah, so gate to substrate capacitance we talked, we said that is the same as the MOS capacitance that we've already discussed at length.
It's apart from that, so there is one more capacitance, the inversion, entire body for inversion.
Okay, so you're saying that there is another capacitance that appears from gate to body.
So from inversion to body.
From inversion to body, but that is the same medium. How can there be a capacitance between inversion layer and the body? That is all silicon. Any charge needs to flow, it will flow.
There is a depletion between inversion and body. There is a depletion. So
depletion
there is
is
a small capacitance.
But current flow can happen. So between inversion and the silicon body, there is no capacitance. Cannot be, because they are connected. Charge will flow. Charge flows.
I have seen in a diagram.
So if the inversion layer is not there, so don't get confused. If the inversion layer is not there, then we say that gate to silicon surface and silicon surface to edge of depletion, there are two capacitances in series.
Yes.
But at that point, there is no inversion layer. There cannot be a capacitance between inversion layer and the edge of the depletion region, because they are electrically connected. Okay. So yes, Meher?
Yeah, I mean, adding to Madhur's point, I didn't understand that if there can be a capacitance between your source and your substrate, because of the same reason, due to the existence of a depletion region, then why can't there be a capacitance between your inversion layer, which is electron
But source
rich?
and the source and the substrate are different dopings. There is a depletion junction in between them.
Yeah, okay.
If there is no inversion layer, then all the silicon is same doping. There is just depletion layer.
right? But then how are we then differentiating your
How will you
inversion
get the
layer, which
charges?
is,
So, okay, for a capacitance, there need to be two plates
yes,
separated by a dielectric,
yeah,
where you could apply two independent voltages at two different plates, and then they are separated by a dielectric.
yes, sir.
So, if there is no inversion layer,
Okay,
where is the plate? And if there is an inversion layer, there is anyway a connection. There is a connection between that part of silicon and the depth. Akansha, you're saying something?
I think she's unmuted by mistake.
Yeah.
Okay, sir. So, yeah, that I got, that when there's no inversion layer, just a depletion region. So effectively, there are capacitors in series. So the effect is that your capacitance gets lower.
Yes.
But so see, when there is an inversion layer, then the region of the substrate right beneath the plate acts like right beneath the silicon dioxide acts as an n-type substrate, right? That's the
No,
point of an.
it is just a layer. It is just a sheet of electrons that starts to appear there.
Okay, so we cannot compare your source and drain with the inversion layer. They're two very different things.
Yes.
Okay.
Okay. So if we look at the top level view of the MOSFET, then this is how it would look. And that is the overlap region and the overlap capacitance that Gagandeep mentioned, that beneath the gate, there is an overlap capacitance. But in reality, let us say there is a contact over here. There will be a gate to contact capacitance, and there will be lines of electric field which would run between gate poly, vertical poly, and the active region, the diffusion region. So what does this mean? This essentially means that in a MOSFET, there is a capacitance CGB, gate and body. There is a capacitance between gate and source and gate and drain. And there is a capacitance between C source and body and drain and body. Are you able to appreciate all these capacitances?
Yes, sir.
Yes, Raghav?
So in the previous slide only, the previous one, sir, can you move there? So this electric field that you're talking about between the poly and the drain, which is coming out, I mean, the electric field should be in the overlapping region, right? But
why?
What is this?
Why just overlapping region?
So diffusion capacitances that you just the overlap capacitance that you talked about.
That is just one component of gate to drain capacitance. That is what I wanted to highlight. Gagandeep talked about just one component, which is the overlap capacitance. But there is this other component of capacitance between gate and drain, which would come with the gate to contact coupling and the gate to diffusion layer coupling.
So this diffusion layer coupling, I'm not able to get exactly what.
Exactly, yahi to dikhaya maine. There is a dielectric here. Let us remove this. This is all is dielectric. This is supposedly a metal equivalent because this is drain. There is this metal equivalent which is poly. So there are two metals. In between there is a dielectric. There will be lines of forces between them.
So what kind of dielectric will be in between this? I'm not.
Silicon dioxide.
So but that is the gate of that is the gate one.
So everywhere is the silicon dioxide.
Okay.
What do you think?
So we are covered.
What do you think? Is there nothing? Is there air between these two places?
It means I didn't had an idea about this.
So this all is silicon dioxide.
Okay.
We talked about oxidation, na?
Yeah. Okay. So we are covering everything.
We talked about oxidation. See, again, see, I am repeating the same thing again, which I repeated in the last session. That whatever we talked about, whether it was fabrication. So why do you think I'm answering all these questions, which supposedly should be answered in SSD and not in DVD? Why do you think I'm taking you through all this?
So you're trying to connect maybe different.
No, because you need to realize that unless you understand things from the very basics, you cannot become a good circuit designer also.
Okay.
Each one of those aspects that we have covered in the class till now, whether it was the design flow and hundreds of questions you asked around the design flow, or whether it was the fabrication flow and the so many questions you asked around the fabrication flow, or this band bending and everything. All of this you need to understand to be able to use transistors effectively and become a good circuit designer. This course is about circuit design. Therefore, these are the incoming inputs. अगर आपने courses नहीं करे हैं, then you need this kind of knowledge. Don't assume that it was an independent topic. सर ने तो BDF का introduction दे दिया था बस. No. I would rather not have given that introduction if it was not needed for this course.
Right, sir.
Okay.
So sir, this gate to drain capacitance in the model, that was consisting of this overlap and this also this
yes,
coupling, the other coupling.
The total CGD would have both components in it: the overlap capacitance and the gate, the polygate to metal and to contact, and polygate to diffusion layer capacitance. Everything will be there in the total CGD.
So just one more thing, in the gate to drain, we are basically comprising 3 capacitances, right? So overlap, contact, and this above.
Diffusion layer, yes.
And same goes for the gate to source also.
Yes, gate to source. Similarly, gate to body. You know, in different regions. For example, if there is inversion layer, then the gate to body capacitance is something. But if your device is off, then the gate to body capacitance could be something else.
Yes, sir. That's the MOS capacitor behavior.
Because the depletion layer would also come into picture there. So whatever components would come. When we say CGD, you should mentally or be able to relate, oh, all these 3 things would contribute to the capacitance. So if I tell you that, my friend, please reduce CGD, what would you do? As a designer, can you control this?
I don't think so, sir.
No, but as a designer, you can control the spacing between contact and this. As a designer, you can control the overall diffusion region. So as a designer, you can reduce the density of contacts, and therefore you can control the poly to drain, poly to contact, or let us say gate to drain capacitance.
So what do you mean by the density of contact? Just is mentioned.
We will see once we look at the layout.
Okay.
Abhi just park this.
Okay.
Okay. So this is the top. Let us abhi bhi dekh lete hain. So this is the top level view of the device.
Yes,
poly
sir.
And source and drain. So I can make multiple contacts over here.
Yes, sir.
So if I say that no, I will not make 2 contacts, I will make 1 contact. I will reduce the capacitance now, because I've reduced the area.
Right.
So that was what I meant by reducing the number of contacts. So as a designer, you can do this. So until you understand that all these 3 components exist, you will not be able to handle the requirements of the design effectively.
Okay. Right.
So do not think that this is only theory. There is a clear application of what we are talking about.
Okay. So sir, I can reduce the number of contacts. That is between the 3 components, I only have one component which I can play with.
And I also said you can reduce the drain region, the drain area.
So drain area I can reduce now, because that is.
So if there is this device, I can say, oh, I will just make it this big. I will not extend drain unnecessarily.
So I mean, drain, as we have made some layouts, it is dependent upon the active region, right?
Yeah. So active region, you can keep it to the minimum width, no? Not just let it run hundreds of miles.
So, but that is basically controlled by the sizing that we want to achieve.
This extension I'm talking about.
Okay. So I'm not aware of this parameter, right?
Yeah. So we will see. You will become aware pretty soon. You made the layouts now. In the assignment also you're making layouts.
Yes, sir. Sir, but this,
How are you not aware of this extension?
Sir, I'm not controlling this because actually.
Why?
Sir, I mean the width I'm controlling, so it is.
Oh, you're
bigger.
using P cells to design your layouts.
Yes,
Am I
sir.
right? You're using P cells to design your layouts.
So
You're
I'm
invoking a PMOS and an NMOS directly.
yes, sir. Yeah.
Then you're automatically giving away the control that you would have had to the tool. Na? You make the layout by hand. Make the active region, make the poly. You will have all the control.
So right now, when we have done the schematic, then we do like generate from source and we get PMOS and MOS.
Don't do
and
that.
Then we do.
So don't do that.
Okay.
Who said generate from source is the only way? Open a virtuoso window and make the active and make the poly.
Okay.
You have all the controls with you. आप खुद ही control दे रहे हो tool को आसानी के लिए. So how will you control? You're giving away a lever, a design lever.
Okay. Okay, so we can keep it to the the minimum BRC that would enable it. Okay.
Yes.
Yeah.
So there are. So you have two levers. You thought you had none.
Okay. Okay. So that will basically minimize that basically the coupling one, the gate to drain coupling. If it is this. Yeah.
Yes. See, the overlap you have no control over. Overlap capacitance is a technology feature.
Fabrication.
है ना? Because that is what is required to ensure there is some VT, some whatever. That you cannot control.
Okay, sir.
But whatever you can control, at least you should be aware of that.
Right. Yes, sir. Okay.
है ना?
Yes.
So this is how the gate and the various capacitances, are kind of seen over here, where we say that the C gate is EOX by TOX into width of the device into length of the device. This is clear?
Sir?
Yes.
Sir, a small question, sir. So while you were mentioning about the pins on the drain and the gate, you said that there might be more than one pin. I'm like, why are we taking? Yeah, sorry, contact. My bad. So why are we taking more than one contact, sir? Actually, I'm like, firstly, why are we taking more than one contact, and why are we again?
You do a P cell, you make a P cell, and make a device of width 2 microns. See how many contacts it will give you.
Yeah, sir. Actually, I've made that, but it has given many contacts, sir. I'm like, that was my doubt.
That is what I'm saying. Remove them.
I'm like, I should remove those.
Not all of them. Few of them.
You mean to say I have to connect them by each other or something, sir?
Remove them. What does remove mean? Does remove mean connect?
No, not as such, sir. Okay, sir.
Remove means remove.
I'm like,
instead of 10 contacts, use only 4 contacts. Use only what is needed.
Okay, sir. Okay. Thank you, sir. I'll try it.
Now, why are 4 needed? Why is 1 not sufficient?
Actually, that was my doubt, sir. I'm like, I didn't know why are we, I'm like specified about the number of contacts exactly. I'm like, why are we even looking into it exactly?
You tell me. What are contacts? They are kind of wires connecting the metal one with the source or the drain.
Yes, sir. Yes, sir.
So if you have 1 wire versus you have 4 wires in parallel, what happens?
Okay, resistance decreases. I don't. Got it, sir. Thank you, sir.
Okay. So what is being shown over here is that as VGS changes, there is you can actually end up seeing different capacitance on the gate. Why is that?
So the above graph seems to be of the MOS capacitor itself.
Yes. We've already done all of this. Okay. Above graph shows the depletion region being formed, and therefore the change of charges happening at the boundary of the depletion region. And as soon as the inversion layer comes, independent of frequency, we at once have high capacitance.
So what is this lower graph then?
These are the 2 components. This is the gate coupling with body. because depletion region was coming into picture. And as soon as the inversion layer is formed, there is no further coupling between body and gate. Now the additional charge comes from source and drain regions. Remember, in the inversion layer, we said that in devices, in MOSFETs, the source and drain will give the additional charge even at very high frequency.
Okay, so but in the lower frequency, when the inversion is forming, the charge is coming from the body itself, or is it and then also coming from source and drain?
You see, we've already shown it like this, that it is coming from source and drain. It is closer, na?
But it is showing that when VT has reached, I think so, then it's coming from source and drain.
So this is the VT point.
Right.
This. Great. So this line is the VT point. You see, already this capacitance has started to rise before that. What does that mean?
The charge, the inversion is forming due to the source and drain.
Yes.
So the lower graph is just basically elaborating that where that components.
They are components. This is component. There are various components. This is capacitance with bulk. This is capacitance with source. This is capacitance with drain. It's saying that all the three components add up to form CGC, gate capacitance. And source and drain, they have equal coupling because of equal overlap and equal density of charges there. Therefore, this is double. Overall CGC is double of CGS and CGD.
So, but this CGS is basically due to the overlap, right? Or is it also like all the three?
अभी तो हमने बात करी, it is because of all three, ना?
Okay. Okay.
है ना? Vaishnav? Vaishnav, you have a question?
Sir, sorry, sir, I forgot to.
Rajneesh?
Sir, in this first graph, sir, here this gate to source and gate to drain both are becoming after this VGS is greater than VT. Sir, they are becoming half. Sir, is this because of the uniform channel formation?
Yes, because VDS is kept at 0.
Okay, sir. Sir, after this, in this, sir, this saturation, nothing is told about this saturation. In
that
this
is the second graph. That is the graph on the right side.
So if we increase this VDS, so this VGS and VGD both will become 2/3 increased in the first.
No, due to pinch off, the drain will have no influence. Therefore, the gate to drain capacitance goes towards 0.
And this gate to source will become 2/3.
Will increase, yes.
Yes. Okay, sir.
Okay.
In the same graph.
Yeah, this one.
No, sir. In the left one.
In the left one, VDS is equal to 0. So there is no pinch off happening.
So suppose
both
at the end
equal.
of So suppose at the end of this graph, in the first graph, we start increasing VDS. So then what will happen to VGS and
VGD? That is what we have done over here, na? We started introducing VDS. That is what happened.
So that's the continuation of it. Okay. Yes.
Yeah.
Yes.
यही तो है. Notice same points हैं. WLC ox by 2, WLC ox by 2. Same तो है. फर्क क्या है?
Yes. Okay.
Okay. Rajat?
So in here we have written a C gate to be just depending on the thickness of the oxide. So here it would actually depend on other factors also, no? So
yeah. That is where the graphs are there, na?
Yes, sir.
Meher?
Yeah, sir. This refers to before. So you told us about the three components. I got the contact capacitance and the coupling capacitance. That's fine, but didn't quite understand the diffusion layer capacitance you talked about.
We'll come to that.
Okay. And second question is, in this graph, you see we are seeing the components GCS, GCD, and GC bulk. But yeah, I mean, when we had studied the MOS capacitance, we were only, in a sense, I mean, from what I understood, we were only looking at the gate to bulk.
Because there was no source or drain there.
Yeah, but here we see that the gate to bulk capacitance keeps decreasing.
It vanishes. So it decreases for a MOS capacitance also. No? That is where we end up with the depletion region, where we go to WD max and we say this is the minimum capacitance you would have.
Yeah, but then it increases, right? But in this,
only in low frequency, when the change is happening in the inversion layer again.
But then, sir, I mean, even at high frequency, then after one point it remains constant.
But that is low. That is a low value.
That's low. But in this case, we just see it just keeps on decreasing until it vanishes. So
but
how
that
does that
is the
happen?
CGCB.
Okay, and
but because charges now start to come from source and drain region, therefore gate capacitance comes up.
Okay, so when you're talking about the bulk, you're talking about the substrate
only, the
not
substrate.
between inversion layer and gate.
No.
No. Okay. Okay, so
okay. So now we come to the diffusion capacitance. That was what you were asking. What is happening with the diffusion capacitance?
So can I?
You are explaining this?
No, no, sir. Sir, I want to ask about the rightwards graph, the graph on the right side. I was not able to understand that.
Yeah, tell me.
So here we were saying the GCD is decreasing and GCS is increasing. Why is that so, sir?
Because pinch off has happened, so the drain is no longer connected to the inversion layer.
Okay.
The drain can no longer, so when you change the gate voltage, there is no longer any change in the charge towards the drain.
Yes, sir. That is why
CGD goes to 0.
Okay. And at the source side, we have the charge density. That is why it is increasing.
Yes.
Okay.
Now all the charge needs to come from the source side only. Therefore, the component or the value of CGCS increases.
Okay, sir.
Okay. But because pinch off has happened, the overall inversion layer width has reduced, or inversion layer availability has reduced. Therefore, the overall capacitance is reduced.
Okay.
Okay. So now coming to the diffusion capacitance. Are you able to see this tub over here? I'm calling this a tub because this actually looks like a bathtub or a tub for that matter. Which is where we have doped N plus for the source or drain region, let us say. Now, if I say that this is one plate, there is a PN junction on all the sides of this plate. Are you able to see this?
Yes, sir.
All the sides except this one. Why?
Because there is depletion layer.
Depletion तो इधर भी था.
So inversion layer.
Yes, because the channel is there. There's an inversion layer that we are talking about. Okay, if there was no inversion layer, then it would come on this side also. But in an on device, they say there is an inversion layer, so this will not appear. So if I want to find the capacitance of this drain or the source, what happens? I have to measure the capacitance on the side walls, and I have to measure the capacitance of the bottom tub, bottom of the tub. Are you able to see this?
So, but the side walls is like on the side walls you have the dioxide, right?
Side walls, you have the, okay. So let us look at, wait. So side walls, you have this isolation, yes, but this is there, no?
Okay, sir. Yeah, didn't notice.
Okay.
Yeah.
Sir.
Yes.
So on the channel side, the inversion layer is just at the surface, but I have got that WD max. So that would also count now because it's not WD max is there. So I will get that.
See, on that side, even though there is a depletion layer, there is no other end of the plate. because of the channel and the depletion layer. So let us look at it like this. Over here, so what are we saying? That there is a depletion layer over here, and then there is a depletion layer WD max over here, and then the source comes.
Yes, sir. Yeah, sir.
So where is the other plate now?
So the substrate itself will be the other plate, right?
That is too far away. In fact, there would be there is an easier way to flow charge from here from the inversion layer and so many places.
So is it like that? It is becoming like negligible kind of thing because of the too far.
That capacitance. So capacitance of this part of the plate to this part of the plate. It is such a big, long path. The dielectric thickness is so long. T oxidity depth कह देते हैं. It's so big that the capacitance is insignificant in comparison to what you will see over here.
Okay.
So what do? We say that, okay, let us measure the perimeter and then multiply it with the number, which is C junction side wall. Okay. And let us measure the area, that is the extension and the width. Okay. So this is LS, the extension and the width. That will give me the area of the bottom rectangle, and I multiply that with C junction. And with this, I get the overall capacitance of the diffusion capacitance of the drain or the source region. Now again, if I want to reduce the drain or source capacitance, what do I need to do? Width is fixed, but I can reduce the LS. Are you able to see this?
Yes, sir.
So this diffusion capacitance is the gate to bulk, source drain to bulk and the source to bulk. This is in the model.
Yeah.
And so one more thing, say in the junction capacitance of the like side walls, the way is this XJ parameter coming into picture, because it should also be there now for the parameters. We had it only 2LS plus W.
Yeah. So you will say that CJ into XJ becomes CJSW.
Okay.
Because substrate तो वही है. You know the depth, and based on that, you came up with this value of CJSW.
Okay. And so one more thing, so this LS component will have that overlap component also, right? Because that is there, right? Or it will be subtracted.
Yeah. LS would be the entire drain region, whether it is below the gate or not below the gate.
Okay.
If there is a junction existing there, so इसमें overlap की बात ही नहीं है राघव.
Yeah.
Overlap तो ऊपर वाले surface पे हो रहा है.
Right. Yeah. Yes.
Okay.
Sir, so you said that diffusion capacitance is a component of your gate to source or gate to drain capacitance, but in this case, it seems like it's a component of your source to bulk.
No. Oh. So I did not say diffusion capacitance. I said gate capacitance with the diffusion region.
Okay.
What I meant was those extra lines of this was, am I audible?
Yes, sir.
Yeah. This was gate capacitance with the diffusion region.
Okay, sir.
The diffusion capacitance, when we use the term diffusion capacitance, this is what is the diffusion capacitance that we're talking about. Okay.
Yeah. Yes.
So the diffusion term is coming because of the fabrication thing, right? Because we should diffuse the layer.
Because initially the source and drain regions were diffused.
Okay.
That's why it is coming. Today they are implanted. Today the ion implantation is done. At an earlier point of time, phosphine was run through and diffusion happened. So that is why we called it diffusion layer. So purana naam chal raha hai. Okay. So now we come to the next.